Hello, this is question 4 from the 2011 MAT. We got let Q denote the quarter disk of points x, y. So not a circle, a disk, such that x and y are both greater than or equal to 0, x squared plus y squared is less than or equal to 1, as drawn in these two figures. Right, on the axes in figure A, sketch these graphs. What's the largest value of x plus y achieved in these points in Q? Justify your answer. Right, so what are we sketching? X plus y is a half, x plus y is 1, x plus y is 3 over 2. So in other words, y equals a half minus x, y equals 1 minus x, and y equals 3 over 2 minus x. So they're all straight lines going through, well, they're going to go through a half, go through 1, go through 3 over 2. They've all got gradient minus 1. So let's try and draw these in. Actually, this is, yeah, it's not too bad considering trying to draw on this screen. Right, so that's those. Middle one's a little bit wonky. What's the largest value of x plus y achieved at points x, y in Q? So how big can x plus y get inside the disk? So x plus y, this is going from a half to 1 to 3 over 2. So we're increasing as we're going out. So we want to have the largest value. Okay, right, so from the diagram, so from figure A and symmetry, because we've definitely got symmetry going on here, because this is going to get a largest value when this is just touching. When it's tangent here at x equals y, we're going to get a maximum x plus y when x equals y and it's on the edge of the disk. X squared plus y squared is equal to 1. Right, so we just need to solve these then. So that's saying, therefore, we've got 2x squared equals 1. X is then going to be, well, root 2 over 2. And what we're trying to do, the maximum of x plus y. So maximum x plus y is going to be 2 lots of root 2 over 2. So root 2. Okay, right, so that's part 1. Next bit, part 2. On the axes in figure B, we've got 3 more graphs to sketch and then a couple more large values to work out. X plus y is a quarter, x plus y is 1, x times y, I should say. X times y is a quarter, x times y is 1, x times y is 2. So y equals 1 over x, the middle one. I'll draw that first. So if we got a half, that will be 2. So it's got to go through there. If it's 1, it will be 1. If it's 2, it will be a half. So this is going to be a lot harder to draw up on this screen to connect these up on here, but you get the idea. And then we got double that. So that will go through there. That will go through there. We'll have some value in between. So this will be a bit flatter. They get flatter as you multiply them out, at least in this section of the curve. And then a quarter of that. So that will come down to about here. That will come down to about there. That will come down to 0.5, 0.5, and then we'll just try and make it symmetrical. So it's going to be a much sharper curve. Again, you'll be able to draw this out better if you've actually got a bit of paper. Right, so let's draw those. What is the largest value of x squared plus y squared plus 4xy achieved at points x, y in Q? So the largest value of these things put together. Right, so these things are moving out again. So this is telling us what's happening with x, y as we're moving them outwards. So x, y increases as we move out, and so does x squared plus y squared. So these things just keep on increasing as we're moving these out. We're going to get a largest value again when they're the same, when x is equal to y. So again, we're going to get a maximum when x squared plus y squared is equal to 1 and x is equal to y. So that means we've got, well, we need to work out where this thing's going to hit on the edge. Well, it's going to hit in exactly the same place as it did before. So that's going to be when x and y are root 2 over 2. Okay, so what am I trying to work out? This thing here. So x squared plus y squared. So the maximum of x squared plus y squared plus 4xy is going to be 1 plus 4 lots of xy. So 4 lots of root 2 over 2 squared. So 4 lots of a half. So 3. Okay. Oh, we've got another one to do. Largest value of x squared plus y squared minus 6xy. Right, so what is that going to be then? So we want to, well, we can minimize. So for this one, for x squared plus y squared minus 6xy, we want to minimize 6xy and maximize x squared plus y squared. So we can do that by, actually we're going to have this in 2 places, aren't we? We could say, if we make this 0, so if we said x equals 0 and y equals 1, then we'll get 1 minus 0. Or we could have x equals 1, y equals 0, in which case we get 1 minus 0. So that's going to be 1 then. We can't do any better than 1 on that, because we know x squared and y squared can't go beyond that, and we can do that while achieving that being 0. Okay, right, that was kind of wandering way through. I filled up the sheet, so let's get a new one up for the last part of the question. Describe the curve x squared plus y squared minus 4x minus 2y equals k, where k is greater than or equal to minus 5. So, well, that's a circle. Let's get on the right sheet. So this is a circle. The center is going to be 2, 1. Center 2, 1. And then we're going to have to take 2 squared and 1 squared off 5, add that to the other side. So the radius is going to be the square root of k plus 5. Yeah, k plus 5. Nearly said minus, but it's going to be plus. So that's why they've got k is greater than minus 5. Otherwise, we're just going to have a dot. We're not going to have a circle. Okay, so that was fine. What is the smallest value of x squared plus y squared minus 4x minus 2y? All right, so this circle, smallest value achieved at points x, y in Q. So the smallest value of this circle inside Q. So this is a center 2, 1. So let's mark it on one of these then. So we've got a circle with center there, that's 2, 1. And it's got some radius, but we don't know what the radius is. So, okay. So what am I trying to do here then? So we want the smallest value of that achieved inside those points, right? Okay, so we've got this k. So what's this? So as k increases, the radius increases, the circle is increasing. So yeah, as k increases, that means that x squared plus y squared minus 4x minus 2y increases. So we want to have the smallest value. We want the smallest possible radius. Therefore, we want to find smallest radius at which the circle and the disk intersect. Circle and disk intersect. Right, so that is going to be when the centers are in a line with the touch point. So that will occur. So we've got to have we've got the center there, we've got a center there. We want to connect the centers, and then we want to find that point there. So this occurs, i.e. the touch point, on the line between centers. Right, so this should be quite straightforward now, I would have thought. We know that that length is 1, that radius there. The distance from the origin of this center is going to be 2 squared plus 1 squared all square rooted, so that's root 5 on the outside. So this distance here, so therefore radius of circle is equal to root 5 minus 1. Okay, because that's the bit that's left. We've got root 5 all the way from the origin up to the center of the circle, and we take 1 off for the radius of the disk. Okay, so that is our radius. So, and that is equal to root k plus 5. So we've got the square root of k plus 5 equals the square root of 5 minus 1. So we square both sides, k plus 5. So that would be 5 plus 1 will give us 6 minus 2 root 5. And then we take the 5 off. So k is going to be equal to 1 minus 2 root 5, which is still happily greater than the minus 5 that they wanted there. Right, I think that's it. What is the smallest value of that, which is the circle? So the smallest value of k achieved at points of those. Yeah, that's fine. Okay, that was quite a nice question, all in all. Again, a little bit, felt like I was stabbing in the dark a little bit going through it. I didn't really know where each bit was going to end up, but you can talk through quite nicely each section of it. And the symmetry stuff is really important, and it comes up so often in geometry. You know, there's no difference here between x and y. In any of these equations, you could interchange x and y, all of these three here, all of those there. In fact, everything. As soon as you're on a circle or a disk, in this case, x and y, they're indistinguishable from each other. So whenever we're finding any of these maximum or minimum solutions, then, well, with the exception of the last part, but for the other parts where it's all symmetrical, then they're going to be on that line of symmetry where x equals y. It's different in the third part because x and y are no longer the same because we've shifted this circle here off to x is 2, y is 1. So we have to then look at things a little bit differently. But symmetry is a very powerful thing in geometry questions. So yeah, that was a nice one.